Hello, my name is Kumar Shaswat and I'm a PhD scholar in Bennett University. I'm in civil engineering and today I'll present you my project in advanced machine learning, and the topic of the project is structural damage detection and location detection of a structure. Now let's start. Hello. So what we will be covering in this video, I will discuss the motivation behind the project, the scope or the application of this project can be used on, definitions that are basics and required, experimental setup that we used, apparatus that was used, methodology, and then we'll go to machine learning model, problem faced, and the limitations. Motivation. We already have it is already in news that many structures are collapsing without any prior indication that they might collapse. So we need a solution that can model or test a structure if it is damaged or it should be retrofitted or evacuated, right? In every kind of structure, in steel, bridges, concrete bridges and everything. So we needed a basic platform at which this can be done in real time or instantaneously when it is needed. The scope of the whole project. The understanding is detecting if the structure is damaged or not. Imagine a bridge. This is a steel bridge. You go there, you expect the setup, and you can detect if there is a damage or not. And then what we want to do in extra is the questions that will be is where that damage is, how much that damage is. Now knowing all these three factors will help us to plan how to retrofit, how to cover this problem, and if the structure should be rebuilt, should be retrofitted, repaired or not. So these problems and predictions were important, and these things can also be modified into use different applications which require different materials and etc. Even this in SHM, it can be a real-time structure which is situated system in a building to monitor it continuously for any damage induced. It is also possible. Damage detection, localization, damage quantification. Damage localization is pointing out where the damage location is. Damage quantification is how much amount of damage there is. The experimental system. There were three things that we use as a setup. We needed Agilent, the VWE Pro software, LCL meter, PZT sensor, coaxial wire, steel plates, and a drill machine to induce damage. Now, how did we do it? Apparatus, we took 4 stainless steel plates of 304, which are abundantly available and easy to find. Took it in almost the size of A4 size, and the exact dimension of the plates were 27 centimeter into 20 centimeter. The tensile strength of the plate is 700 to 500 MPa. LCR meter, that is inductance, capacitance, and resistance, that is LCR. The software that we are using is to acquire data from the LCR meter, taking it into an Excel form that we can use for further excitation. Now the sensor that is taking all the data is the PZT sensor or the piezo sensor. For each plate, one sensor per plate, right? And coaxial wire to attach, and then drill machine to induce damage, right? What was the methodology? We attached a sensor on a specific location, right? On that location, we mark different, on a different plate, we mark different location of the damage. 4 plates, that means 4 different locations of damage. Now, going back to the first plate, what we did was to take a healthy state of the data, then we go to the damage induced by percentage and increasing. How we did that is, we took the healthy state of the data, then we drilled holes to induce damage, right? Then these plate different location damage percentage was calculated. How did we calculate damage percentage? It is easy. 10 mm holes, right? 10 mm holes, and the width of the plate is 20 centimeter, that is 200 mm. We multiply this both, we get 2000 mm square of the area in which we are reducing the area of the circle, that is will be 314.16 mm square, and calculate the percentage. So what would be the percentage that we use were 15.7, 31.42, 47.12, 62.83, and the distances that were taken was in multiples of 4.5. So the first plate had a distance of 4.5 centimeter from the sensor, then 9 centimeters, then 13.5, and then 18 centimeters. Data was acquired in the form of conductance and susceptance, right? And damage percentage for each damage percentage were taken, right? Data for training was added with label of damage, percentage of damage, and distances of damage from the PCT sensor line. So what are these labels? Damage that is introduced, it is damage or not. It is binary. 1 means there is a damage, 0 means no damage. Percentage of damage. Amount of damage, that is amount of the area that is missing from the allocation area that I've already told you, and a distance from the PCT sensor. So how did the model work? The data was set was in these multiples. The features that were taken was the plate label, conductance, susceptance, damage, binary in binary form, then damage percentage, then distance of the damage. Right. Model used for logarithmic regression for damage detection, elastic net for both severity and location. How did the problem flowchart was is we start, we detect if there is a damage or not. It is if there is no damage, then we don't need no detection. If there is a damage, we localize where the damage is, then how much the damage is there, and then the program ends. It will show the results, and then the program ends. Of course, it will show the results. Now the problems set that we have already you have already noticed would be that there were only 4 plates, right, and 1 validation plate. For there were only 4 plates, we increased the amount for with 5 states. So each place has 5 states. That will be uh, total of 20 states, right? Now this total of 20 states has specific amount, right? How do we increase the amount of data? Is taking each in the each set, there is healthy first hole, second hole, third hole, and fourth hole, with the frequency excitation frequency variation from 30 kilohertz to 1 megahertz. That will be 9701 values of excitation frequency at which where data is taken. Hence the amount of data or rows that I have described. No two data are the same. What is that? Even the first plate and second place healthy states have different signature. That helps us in the modeling process, but it is really hard to model to. It situates a problem and a solution for a different problem. And dataset orientation was also a problem. We cannot treat it as a time series data or apply a heavy model on it. We need it to be a work on any handy device. So we needed less computations and accurate results. Limitations was experimental setups. Of course, it is bulky. You cannot take everything there. But this can be a solution, or there can be solution also by making or incorporating all these parts into one PCT sensor and one apparatus for taking all the data and giving you the damage and distances. Now the range of the PCT sensor bonded is limited. For every material it has a different range. For steel it is 2 to 4 meters, that will cover almost that is in circular area. So we are calculating in 1 dimension. Okay, and the highest model accuracy achieved was 80.12, right? Now this is a problem because the model accuracy was low. Hence when we are taking the values, we take values for a lot of percent, and then we calculate the mean of those predictions, and then we get the results. So accuracy in the validation was quite high, as we got 99.94% for the our detection, 99.9% for our damage severity, and 96.29% for our localization. But the modeling accuracy was low when we check it from test sets and training sets. Thank you.